Hello students, today we'll continue chapter 14 and we reached till inference rules for functional dependencies. Uh, so if we have for example f which we call a set of functional dependencies defined on R, and from this set of functional dependencies we want to determine or get f plus, which is called the closure of f, which is the set of all functional dependencies that can be defined on R, that can be determined from the initial set, which is f plus. So the closure of f or f plus is the set of all functional dependencies that are logically implied by f. So to write it in terms of set, then the closure of f is denoted by f plus, and we can write f plus equals a set. The elements of this sets are functional dependencies in the form x determines y, such that x determines y is implied or logically implied by f, which is the set of functional dependencies. So a big f plus may be derived from a small f. Let's take an example. If we have a relation R of three attributes a, b, and c, and we have f, which is an initial set of functional dependencies. The first functional dependency is A determines B and B determines C. This is the initial set of functional dependency, and we want to determine f plus, which is the closure of f, or the set of all functional dependencies that can be determined from this one. F plus, um, the first thing we will do is copy both these two functional dependency and put them in f plus. So A determines B will become in f plus and B determines C. Also, because A determines B and B determines C, we can put A determines C. This is derived from the transitive rule we will take in the next video or in this video. And we have a reflexive rule that tells us any attribute derives itself. So A defines the A, or A determines the A, B determines the B, and C determines the C. And you can also put AB determines the AB, or BC determines the BC, or AC determines the AC. Also, this is called the reflexive rule. And we have also the decomposition rule, by which, for example, if we have AB determines AB, then we can decompose the right side of the functional dependency into its simple components. For example, AB determines AB, then we can write AB determines A alone, and we can write AB determines B, as we'll see here. So if we try to think about F plus, this is an infinite set of elements or set of functional dependencies. It can end or it cannot end at all. There is almost an element that can be added to this set of plus. Okay, let's take an example, a real example. If we have this relation schema that combines employee with the department in the same table on the same relation, we have the SSN for the employee and the employee name, birth date, and the address, in addition to the department number for this employee, the department name, and the manager SSN for this employee. So here let SSN be the primary key for this relation. So SSN determines all the other attributes in this relation. So SSN determines the ename, employee name, birth date, address, D number, D name, manager, SSN, which we can see here. So F, which is the set of initial functional dependencies given in this question, we have the SSN determines the employee name and the birth date plus the address and the department number, because if you know the SSN, then you can know the name, birth date, address, and the department number. This is the first element in the initial set of functional dependency. The second element is department name. Department number determines the department name plus the manager SSN, because each department has a number. So if we know the number of this department, we can know the name of this department plus the manager who manages this department. So we have two functional dependencies in the initial set. Okay, and I want to infer some functional dependencies out of these. So we can infer the following functional dependencies. The first one, SSN determines SSN, as we say by the reflexive rule that we will take by short in the next video or in this video. A reflexive rule says that each attribute logically determines itself. Also, we have another rule called decomposition. For example, SSN determines an e-name, and this is come from this one. SSN determines the e-name, birth date, address, and the department number. So SSN determines each component of this, of the right side of the functional dependency. So SSN determines the e-name, birth date, address, and the department number. And we write here SSN determines the e-name, and we can write all what I have listed previously. Also, we have a transitive rule which says that if we have an attribute that determines another attribute, and this attribute determines another attribute, then we can say the initial one determines the final one. Like here, the SSN determines the department name plus the manager SSN. This is because SSN determines the department number, and the department number determines the department name plus the manager SSN. So we can write, or we can tell that the SSN determines the department name plus the manager SSN by transitive rule. So we usually write X determines Y logically implied by F. This sign means that this functional dependency is logically implied from the set of functional dependencies, to denote that the FD, or functional dependency X determines Y, is inferred from F. And as we have said that X and Y are subsets of attributes from the attributes in the relation scheme. Okay, now we have a question. If for example all X values are different in all possible or in all possible instances of this relation, does X determines Y in R? So for example, if we have a relation with 5 columns, and we have X is the first column. If all values of the first column, which is in this question X column, if all the values are different in all the rows and in all the instances that can be made from this relation, then does X determines Y or all other attributes? True. This is true because if the X is different from one row to the other, then X is a primary key. Then the primary key will determine all the other attributes. So from here we have got the theorem. If X is a super key of the relation R and Y is any subset of R, then X determines Y in R. This is a theorem, and we will use it later in our chapter. So if you know that X is a super key, then Y, and Y is any subset, then X for sure determines Y. Note that X determines Y in R is a property. Let's take an example for this for more demonstration. For example, here we have the SSN, which is a primary key. Because we know this is a primary key, so it becomes a super key. Then super key determines all other attributes in this relation, which is from e-name till the manager SSN. Note that X determines Y in R is a property that must be true for all possible legal instances of R, not just for the present R of R. So any instance you make from this relation schema, they should all conform to this um, functional dependency. If X is a candidate key, then X determines Y is correct for any subset of attributes of R, and this is shown in this example. Okay, let's take this example. We have a relation with 4 columns A, B, C, D, and each column has values that belong to its domain. For example, column A have values A1, A2, A3, B, B1, B2, B3, C, C1, C2, C3. We don't have C3, and also D. And we want to know whether these functional dependencies are true or not. A is A or does A determines B is true in this relation instance. We will know now. We want to know if A determines B. What we will do is we go to the first row and see what is the value of A. The value of column A in the first row is A1. So if we have A1, then B is B1. So if A1 is repeated in any other row, then B should be B1. If it is not B1 in the other rows, then this is not true. If it is always B1 when A1 occurs, then this is true. So we have here A1 and the value of B is B1. Let's check in the second column. We have A1 and now B becomes B2. So when A1 becomes constant or unchanged, we have B1 is changing the value. So this functional dependency is false. Let's check for A determines C. We have A is A1 and C is C1. We have A1 and then C remains C1. Let's check if we have other A1. We don't have. Then until now A determines C is true, but we didn't finish yet. We have to check for A2 and A3. We have A2. If A is A2, then C is C2. If A repeats again, A2 becomes A2, C remains C2, which is true. We don't have another A2, so A determines C is true till now. We want to check for A3 determines C2. A3 determines, or if A is A3, then C is C2, and we don't have another A3, then this is true. So let's write them. This was false. Sorry. This is false. This is true. Okay, let's check for C determines A. So if C is C1, then A should be A1. Let's check. Here C remains C1, so A should remains A1, which is true. Let's check if we have other C1 we don't have. We now move to C2. If we have C2, A should be A2. If we have C2, A should be A2, which is true. If we have C2, A should be A2, which is not true. So this is false. Sorry. Okay. And we can check also for A determines D, B determines D. Let's check for AB determines D. So I want to check for AB determines D. Okay, let's check. If A and B are A1 and B1, then D should be D1. If A and B is A1 and B1, D should be D1. Do we have another A1 and B1? A1, B1, no. This is not A1, B1. A2, B2, A2, B3, A3, B3. So until now, A and B determines D, or AB determines that D is true. Let's check. A1, B2. Here we have D2. We don't have another A1, B2, so it's true until now. A2, B2, D2. A2, B2. We don't have A2, B2. Now A2, B3. It should be D3 for D. And we don't have another A2, B3. Now we check for A3, B3. It should be D4. And we don't have A3, B3. Then this is true for this relation schema. Okay, and we can also check for AB determines C and AB determines the CD. So by this way we can see whether these functional dependencies are true in this relation instance. So we'll stop now and continue in the next video by identifying the functional dependencies.